A helpful way to frame this talk is stop thinking so hard and start remembering more effectively. On the left, a standard LLM has to grind through a huge computation estimating probabilities across an enormous number of parameters just to decide on something as simple as the next word, like the. That brute force approach works, but it's expensive and slow. On the right is the idea behind engram. When the model has seen something before, it can use a memory lookup to retrieve the right continuation directly. Instead of recomputing everything from scratch, it recalls, and that shift from heavy computation to fast retrieval is the core motivation for the engram architecture. When you ask a model something simple like, "Who is Alexander the Great?" it doesn't actually perform a direct fact lookup. Instead, it has to simulate knowing the answer by running the full transformer computation, deriving the response from learned patterns and probabilities token by token. That's the core issue here. Transformers don't have a native knowledge lookup primitive. So even for a static entity, like a well-known historical figure, the model burns through multiple layers of attention and feed-forward networks just to reconstruct what amounts to a basic entry in a lookup table. The result is unnecessary compute at runtime for information that's essentially fixed. For decades, we've had two very different ways to handle information. On one side are classic engram-style lookups. Basically, a fast, constant time, find it in the table approach. Quick, but not very smart. On the other side are transformers, incredibly capable, but often slow and compute hungry because they generate answers by doing a lot of work every time. The newer idea is to combine them, almost like stapling a 1990s search engine onto a modern H100 GPU. You keep the transformers reasoning, but add a retrieval layer that can instantly pull relevant chunks from memory. That's the key insight here. Conditional memory as a new axis of sparsity. Why compute what you can simply look up? The first step in Architect's Daughter is squashing and hashing, and it has two parts. On the left is compression. We take different surface forms of the same word, like apple, apple, and apple, and squeeze them into a single consistent token. Because this mapping is many to one, it's surjective, and it reduces the effective vocabulary size by about 23%, which saves memory and compute. On the right is multi-head hashing. Instead of assigning each engram to one spot, we send it through multiple hash functions, k different heads, so it lands in several buckets in the embedding table. Even if one bucket collides, the other hashed views help preserve the signal, making collisions less harmful than you might expect. In step 2, the model decides whether a retrieved memory should actually influence the answer, using context-aware gating. Think of it like a bouncer at the door of the residual stream. If the context is a geography test, and the memory says, the capital of France is Paris, the gate opens wide. Alpha is close to 1, so that information flows in and helps. But if the context is about a financial institution, and the memory is Bank of the River, the meanings don't match. In that case, the gate mostly shuts alpha near 0, so the model blocks that memory from contaminating the response. Mathematically, alpha is computed with a sigmoid over a similarity between the current hidden state and the retrieved key. When we talk about sparsity allocation, the key question is how to split our limited budget between memory and computation. On the left, a 100% engram approach leans heavily on stored knowledge, while on the right, a 100% MOE approach leans on compute-heavy expert routing. The curve shows validation loss, where lower is better, and it doesn't keep improving as we push all the way to pure MOE. Instead, performance bottoms out around an allocation ratio of about 80%, meaning the best results come from a hybrid. In other words, pure MOE is suboptimal. The sweet spot is mixing strong brains with a smaller amount of sticky notes memory. In the infinite memory regime, the big idea is that we stop scaling the backbone model and instead scale the external memory. On the graph, as the number of memory slots grows on a log scale from about 10 to the 5 up to 10 to the 7, the validation loss keeps dropping. That means the system is effectively gaining capacity by storing and retrieving more information rather than cramming everything into parameters. The punchline at the bottom captures it. with a fixed MOE backbone around 3 billion parameters, memory can add capability without increasing compute cost in the same way that making the model larger would. So, when someone asks, is 100 billion parameters enough? The answer here is not if you can keep adding memory. Here's the plot twist. The boost from engram isn't just about memorizing facts. On the left, we see the expected win. Trivia style knowledge improves over the baseline, with MMLU up about 3.4 points. That's the cheat sheet for history class effect. More stored information, better recall. But the surprise is on the right. Engram also lifts performance on tasks that rely less on recall and more on thinking. Hard reasoning benchmarks like BBH jump about 5 points, and even coding on human evil rises around 3 points. In other words, adding better memory doesn't only help the model remember, it seems to support stronger reasoning and problem solving too. Memory helps reasoning because it lets your brain stop wasting effort on the small stuff. In the standard model on the left, your mind is cluttered with static details, how to spell a term, the exact syntax of a variable, or basic definitions like what is Python. When those facts compete for attention, it's harder to do real thinking. In the engram model on the right, those stable patterns get offloaded to a reliable lookup system, an engram. That frees your working memory to focus on logic and problem solving, like solving a differential equation. The takeaway is simple. Don't sweat the small stuff, store it or look it up so your brain can concentrate on reasoning. Here's the evidence for a shortcut mechanism. The CKA similarity heatmap compares layers in engram to layers in the MOE baseline, and the strong diagonal band tells us many layers are doing similar kinds of computation. What's especially interesting is the shift. Engrams earlier, shallower layers line up with much deeper layers in the baseline. Logit lens points to the same story. Engram starts producing task-relevant signals sooner, as if it's skipping the usual figure out the representation stage and jumping straight into useful processing. In other words, the model is taking a ladder. Its effective depth ends up greater than its actual depth because it reaches deep features faster. A key idea here is keeping the GPU focused on compute, while the CPU and host RAM handle the heavy storage. Think of the embedding table living out in host RAM, and the CPU acting like a runner that brings over exactly the embedding chunks the GPU will need next. This works because the access pattern is deterministic. We can predict which rows will be used and prefetch them ahead of time, instead of making the GPU wait on memory transfers. The result is a lazy GPU that stays busy and efficient even when a massive 100 billion parameter table is offloaded to CPU RAM. With good prefetching, the overhead stays under about 3%, so performance remains high while memory pressure on the GPU stays low. Looking ahead, we see conditional memory becoming an indispensable primitive for next-generation models. The idea is simple. Instead of treating memory as a single, always-on buffer, models should be able to store, retrieve, and apply information only when the right conditions are met, so they stay efficient, consistent, and context-aware over long interactions. Over time, that kind of capability can shift what the model needs to recompute versus what it can reliably remember. In fact, we can imagine a future where certain routine skills, like multiplying, fade into the background because an engram module called Moxity handles them automatically. If you'd like to explore or build on this, the code is available on GitHub at DeepSeek AI engram. When aid